Hello, my fellow geeks and nerds. Kristi here, and time to get our geek on, learning this time about crosstabs and non-parametric tests, although most of it's going to be focused on crosstabs. I'm in a really big hurry today, so this isn't going to be a very fancy lecture, and I won't have time to drop in a lot of exciting visuals, so you're going to have to just deal with the slides and the sound of my voice. Getting started with the lecture right away. How can we organize our data to see if there is an association or a relationship between variables? Routinely, we're going to be using these terms, dependent variable and independent variable. The dependent variable is the thing we are trying to explain, and the independent variable is the thing we think might explain the pattern. For instance, if we look at someone's party identification and then we look at their vote choice, we would assume that people's party identification will inform their vote choice. Therefore, partisan identification is the independent variable, and we're trying to predict their vote choice, which is the dependent variable. Another way to think about it is that sex could be the independent variable, men and women, and we're trying to predict how they're going to vote for a candidate. We're going to talk about these one-way directional relationships, but there are ways that we can use our measures to quantify what we think is a relationship that goes in two directions, which is more complicated than we need to get into for today. We're all quite used to seeing the distribution of frequencies. Now, this example I'm going to be using is entirely made up. This is not real data. This is just for the purposes of an exercise. But if we look at the frequency with which, let's say, men and women appear in our sample, we can have this display here where there are 93 women in our sample, making up 46.5% of the total, and we have 105 men making up 52.5% of the total. I'm not going to go through the percent and the valid percent and the cumulative percent. I just want to discuss the way that we can display frequencies, and I will get on to valid percents later on. In this very made-up example, we're going to be looking at the way that we can use sex to predict somebody's health rating. In the frequency table here, we can see that in our sample, 51 of our 178 participants said they rated themselves as unhealthy, 56 rated themselves as healthy, 71 rated themselves as very healthy, giving us a total of 178 observations in our data set. If we look at the distribution of the cases within their own variable, within sex or within health ratings, we can't tell much about the relationship between someone's sex and how they perceive their health. So to learn more, we use a cross-tabulation, or sometimes, very rarely, it's called a bivariate table. When we look at the distribution of health rating by the sex of the student, we can see there are some patterns that we can pull out. Here we have, in the female column, 34 women out of 80 said that they rated themselves as unhealthy, 29 rated themselves as healthy, and 17 rated themselves as very healthy in this entirely fictional example. In the other column, men, 16 of the 97 rated themselves as unhealthy, 27 as healthy, and 54 rated themselves as very healthy. Those two totals of 80 and 97 add up to 177, as do the three observations of health ratings, 50, 56, and 71, total up to 177. When displaying information, independent variables should be placed across the columns, and the dependent variables should be in the rows. That way, it's consistent when people go to interpret it. Our cross-tabulation, our bivariate table, now gives us what is called the joint frequency distribution, a name you don't need to memorize, but it basically describes the fact that you have two frequencies that have been distributed jointly on a new table. One of the things that we are going to be looking at is which category is the modal category in each independent variable. That is to say, which is the most common response given by that subset of respondents. In this completely fictional example, the modal category was unhealthy for women. 34 women out of the 80 rated themselves unhealthy, whereas the modal category for men was very healthy. 54 out of the 97 men rated themselves as very healthy. This notion of a modal category, or the most popular answer, is going to help us better estimate the relationship between the two variables. In this observation, and in most observations, the number of cases we have for each independent variable category, man or woman, are not equal. Therefore, how can we work with this data in order to understand whether or not there is a relationship between the two variables? We do this by using what is called measures of association. The answers that we want to provide is how do we interpret our data to determine if there is a pattern, and if there is a pattern, how strong is the pattern? The first thing we can do is compare the modal cell. The cell is the column which has the most cases. And as we saw, women's modal category is unhealthy, men's modal category is very healthy in this entirely fictional example. We can also examine the strength of the relationship by looking at the proportion or percentage of cases in each column. In particular, we're going to be looking at how we calculate a lambda. This will answer the question, is there a strong relationship or a mild or weak relationship between our two variables? Since using adjectives to describe things can be quite subjective, it's important to find a quantifiable way to describe this relationship so that comparisons that are identical in how they were calculated can be used to evaluate, let's say, change over time or differences between samples. What we're about to do is to find an objective way to assess the strength of an association between our independent and dependent variables. A measure of association is a descriptive statistic that quantifies a relationship between two variables. It indicates in quantitative terms the extent to which a change in the value of one variable is related to a change in the value of the other variable. Calculating a lambda allows us to generate a number that will fall somewhere between 0 and 1 in an objective way. This measures the numerical difference between our observed data and each of the two possible extreme situations, the first being no association, the second being perfect association. Lambda is one of a number of PREs, or proportional reduction in error measures. The logic of this and all PRE measures is that if two variables are associated, then we should be able to predict the score that a case has on one variable on the basis of the score it has for the other variable. In other words, we should be able to predict the value of what the case is going to be on the dependent variable when we know the score on the independent variable. If sex and self-health rating are related in this fictional example, then we should be able to predict a student's health rating by knowing whether they are male or female. The stronger the relationship, the more accurate our prediction will be. To calculate a lambda, we try to predict how the cases will be distributed in a bivariate table under two conditions. We predict the distribution of cases along the dependent variable without any knowledge of their scores on the independent variable. We predict the distribution of cases along the dependent variable with knowledge of scores of the independent variable. To think about how we calculate a lambda, the first thing that we should imagine is a spectrum with two ends of association placed at each end. On one end is no association. There is no relationship at all between these variables. On the other hand, you could have a perfect association. Knowing information on one will give you perfect information on the other. We're going to be using this notion of the perfect association to help us estimate the strength of a relationship. The assumption here is that all cases within a particular value allow us to know with perfect certainty the value of another variable. In this case, we're going to pretend as if knowing a student is male or female allows us to state with perfect certainty which category they will rate their health status. Now you'll notice here that we've basically turned the modal category from the previous distribution into an entirely perfect association. In the next slide, we'll assume there is no relationship between our two variables. For each category of the independent variable, you would get the same pattern of response that exists for the dependent variable. In other words, what would our distribution look like if our independent variable in no way helps us get a better understanding of our dependent variable? The way we do this is through percentages. So we look at what the percentage is on every single count, and we then multiply that percentage by the number of observations we have, so by 97 men or 80 women, and then we put the raw number in its place in that crosstab space. So here you can see that when we have 28% of the distribution of responses in unhealthy, because that was the overall sample mean, you've got 22 women classing themselves as unhealthy and 27 men classing themselves as unhealthy, because each of those make up 28% of the total observations that we have for each sex. A way you can think about this is, a guess the answer kind of game. If there were students lined up outside the door and all you knew was that the most popular category that students had rated themselves in that group stood outside your door was very healthy, and you got $1 or a pound or a euro every time you guessed somebody's self-health rating correctly when they walked in the door, this is an example of the sort of way we're going to use these associations. So if, in our example, we guessed all 177 students rated themselves as very healthy because that was the most popular answer given, then we would make a prediction that we would get 106 errors out of that sample. That 106 errors of people who rated themselves anything but very healthy, we call E1. So E1 is made up of the 50 people who rated themselves as unhealthy, the 56 people who rated themselves as healthy, because we've already picked the people who rated themselves as very healthy correctly. So what did we get wrong? That total is our E1. Now we include the information about a person's sex to use the perfect association rule. In other words, we're going to assume that the person's sex is going to tell us how they're going to answer. So using this new information about whether or not the person coming into the room is a man or a woman, and knowing that the women in the sample classified themselves as unhealthy more often than not, and the men classified themselves as very healthy, we can then, every time we see a woman come in, predict unhealthy. Every time a man walks into the room, we would predict healthy. And then we ask how, if we get it right, we get a pound. If we don't get it right, we don't get the pound. Well, when you have the information about the relationship between sex and the self-rating, do you make as many errors or do you make fewer errors? And when we total it up based on this imaginary sample, instead of making 106 errors, we would make 89. This new error is called E2. And E2 is made up of the 2 observations of the women who classify themselves as anything other than unhealthy, and the 43 men who classified themselves as anything other than very healthy. Those would be our errors. So we call that E2. A lambda will tell us the extent to which we make fewer errors when given this extra information, our independent variable, about each student's sex. When we do the subtraction, when we subtract E1 from E2, we find the reduction in error due to our using the information in the sex variable reduces our errors by 17 observations. The lambda calculates this reduction in error as a proportion of E1, where E1 is the number of errors without the information for the independent variable, and E2 is the number of errors with the information for the independent variable. Thus, as a proportion, our error rate has been reduced by 0.16. So here we have lambda equals E1 minus E2 all over E1. When we add in the numbers from our made-up example, we subtract 89 from 106 and divide that by 106, and that gives us a precise estimate of 0.16. The advantage of PRE measures are that they measure something meaningful, namely changes in prediction error rates, and they have a very specific interpretation. However, a weakness of lambda is that it often underestimates the strength of a relationship, and it's really not a very good measure when there are 2 modal values above 50% because of the way the math works. Our made-up results show that while there is some relationship between our variables, it's not very strong. Sex is not a good predictor in this made-up example of how a student would rate their health. Now, there aren't really hard and fast rules as to what the difference is between a strong relationship and a very strong relationship is, but we can put them into a sort of ranking order from no relationship to a perfect association. That helps us in terms of describing things so that we don't always have to use the numbers, the precise numbers in our reports. So anything, let's say, between a 0.4 and a 0.7 is a moderate relationship. I generally don't tend to give a lot of credence to anything below a 0.3. I think a 2.7 to 0.3 is really the base, and anything below 0.2 is a really weak relationship. Anything above 0.7 is a very strong relationship. We aren't going to be doing SPSS training in the YouTube course, but just so that you guys know, if you do use SPSS or other statistical packages to assess crosstab data and to produce a lambda or other PRE, you are going to be able to look at it in terms of a symmetrical relationship, an asymmetrical relationship with one of the measures as the dependent variable, and another asymmetrical relationship with the other measure as the dependent variable. The reason why the statistical packages give you this is because a computer package can't tell you which variable is your independent variable and which variable is your dependent variable. That's your job as an analyst, is to be able to look at the relationships and know, based on theory and the world, which is independent and which is dependent. Here's a little example of the outputs that the statistical packages will produce. And if you look at the one in the lower left-hand corner that says directional measures, a symmetrical relationship assumes that the causality goes in both directions. I mentioned before about partisanship and which candidate you're going to support. It's possible that you decide to support a candidate and then your partisanship reflects your support for that candidate. For other people, it might be their partisanship precedes their support for a candidate. So if you thought that there was a relationship in both directions, you would use the symmetrical lambda. And if you thought something else was the dependent variable, you would use that one. So it gives you the association of the relationship so that you as the analyst can assess it and decide which is the appropriate measure to use. A lambda is really good for nominal kinds of data, but what if you have ordinal level variables? The logic of the PRE for ordinal level variables is similar to that for nominal level variables, but the maths are a bit more complicated. The interpretation of the statistical significance of an ordinal level crosstab is identical to that for nominal data, and instead of it being called a lambda, instead we use what's called a gamma that's designed for ordinal data, and this provides us with additional information that can tell us if the association between the two ordinal levels variables is positive or negative. Here's an example from a data set. I'm not entirely sure which one because this is a couple of years ago, but we're looking at age cohort and we're looking at whether or not they agreed with the question, young people got no respect these days. And as you can see, the younger you are, the more you're likely to disagree with that. The older you are, the more you're likely to agree with it. Now, the question is, to what extent is age associated with somebody's response to this question? And the answer is, when we come down here to our symmetrical measures, ordinal by ordinal using the gamma, we find a value of, let's just round that negative 0.276 up to negative 0.28. That would say that because the relationship is negative and the age cohort is younger to older, and the question is phrased in a way from strongly agree to strongly disagree, that the negative association comes because the younger you are, the more likely you are to disagree. The more 3 you are on your age, the older you are on your age, the more 1 you are on your strong agree with a statement. So the higher you go on your age, the lower the response value that you give, and that's why the association is negative. And this is why knowing how things are coded is really important. If you have a dichotomous variable, the variable only has 2 categories, then we can ignore that level of measurement and let the other variable determine the choice of analysis. You should also always use the weaker statistic. If you have, let's say, a nominal level variable and an ordinal level variable, it's better to treat both as nominal and be conservative in the way that you interpret your results. Also, you can use a specially designed statistic. There are specially developed statistics designed for various combinations, and you can check in the statistics books to see if there is one for the combination you want to assess. Getting close to the end here, guys, I wanted to just let you know that there are 2 kinds of statistical analysis. You can run parametric or non-parametric tests. Parametric tests are more powerful, but they have more strings attached. There are certain assumptions about what the data has to look like. Most importantly, it has to have a normal curve in its distribution. If you have other questions, I would recommend Pallant 2005, which is a guide to SPSS, but it's a very good introduction to statistics. If you have very skewed data, you don't have a normal curve, you can still test data using what are called non-parametric alternatives. These are less stringent. They don't require a normal curve in the distribution, but they're also not as powerful. They're less sensitive to detecting relationships, and they're less sensitive to detecting differences. Non-parametric techniques are ideal for nominal and ordinal scales. They're incredibly useful when you have small sample sizes. And you should definitely check your data, and I would recommend again Pallant to see if you should use a parametric or a non-parametric test on your data. Here's a quick list of the techniques, but because you guys aren't going to be working with real data, it's a little less pressing that you're familiar with these parametric and non-parametric tests. All right, everyone, that's going to wrap it up for me. I hope you enjoyed the discussion on crosstabs, that you use them in the future to calculate the strength of association for, let's say, men and women's support for Donald Trump, or by region, or by religious identification. You can now calculate your own lambda using a crosstab. How exciting is that? Okay, guys, I've been Kristi. You've been awesome. See you next time for 201 and the qualitative case study research lecture. Bye.